This problem has us modeling and analyzing a system that is undergoing Coulomb friction, as well as forcing, as well as has a spring attached to it. So we're going to do this in two parts. We're going to do an analytic solution to this using the approximations, and we're also going to get a numeric solution in part B, and we're going to compare the two. So we're going to work as much as we can analytically to do the analysis, make sure that the analytic approximation is going to hold. So, as usual, we want to start with a model of our system. So for a diagram, I'm actually not going to use Lagrange's equations here, even though we could. I'm going to go and use a free body diagram to get my modeling steps done in this one. So I'm going to start with my left-hand picture, all the forces that are acting on my mass, and that'll be my free body diagram, and then I will have my kinetic diagram on the right. Okay, so acting on the mass, we are going to be compensating for its own weight, so m times g, and it is in contact with the floor, so there's going to be a normal force from the floor acting on our mass. And we are defining as our coordinate system that x is positive to the right. So we're going to be assuming that the mass cannot go up and down, the mass cannot rotate, it can only travel horizontally here. All right, and we are going to have, also working on this, I'll assume tension. K times x will be that spring force. So when x is positive, the spring is in tension, it's going to be pulling on the mass, and when x is negative, the spring will be in compression, so this arrow should then be pointing to the right when it's negative. And we also have the force, the F of t, so the F naught sine omega t acting on this. And finally, we are going to be now accounting for the force of friction. So the friction force is always going to oppose our velocity. So for example, if we have a velocity to the right, then the friction force is going to act to the left. So this is going to be modeled differently, certainly, than when we have a viscous damper, because this will not be proportional, linearly proportional to the velocity. However, the velocity will come into play here. So we're going to have some mu times n acting on the system. That is from the kinetic Coulomb friction acting on the mass. But the problem with the way I have it written here is as long as we're traveling to the right, this picture is okay, mu n should be to the left. However, this system oscillates. It's going to be traveling right and then left and then right and then left. So if I just say mu n points to the left, I'm now pointing the wrong direction when I'm traveling to the left, when my velocity is to the left. So the actual value mu n magnitude does not change whether I'm traveling right or left, but the direction of this arrow should. So what I can do here, I need the arrow to flip when my velocity is negative. When I'm traveling to the left, this arrow should point to the right. When I'm traveling to the right, it should point to the left. So one way I can model this is I want to, in order to flip the arrow, I am going to multiply this by the sine, SIGN, of x dot. This is what's going to be introducing the nonlinearity into the system when we go to the equation of motion. And there's other ways we can model this as well, but what SIGN is going to do is if I have the sine of something, let's just say it's q, this is going to be basically a piecewise function. This is 1 if q is greater than 0. It's negative 1 if q is less than 0. And at least for the way MATLAB handles SIGN, it's going to be 0 when q is equal to 0. Now, there's other ways we could possibly model this that you might see. So instead of using SIGN, we might say it's x dot divided by the absolute value of x dot. And this might work okay because it is maybe more easily differentiable because we have x dots, we have absolute value. However, the problem is going to be when our velocity reaches 0, we're going to be dividing 0 by 0 and we're going to have a problem. Whereas the SIGN is going to work nicely because if our velocity is 0, it actually should go to 0 because we should only have that friction happening when we have this kinetic motion. So this accounts for all the forces on the mass on the left-hand side. And by our modeling, by our assumptions that it can only move left or right in the kinetic diagram, it's going to be mx double dot pointing in that positive x direction. And I will also define a y direction here for the modeling step for the free body diagram. So I'll start by solving for the forces in the y direction. So on the left-hand side, I am going to have my n minus my mg. And in my kinetic diagram, because I'm saying that it cannot move up or down, I know that it has to be equal to 0. So this tells me in this case the normal force is equal to the mass times gravity. So that's good. It's not going to change in this problem. The normal force is going to be constant. Now I can move on to my sum of forces in the x direction. So looking in the x direction on my free body diagram, I will have negative kx pointing to the left from that spring. I will have a minus mu n sine x dot. And I will have a plus f naught sine omega t from my forcing. And that's equal to my mx double dot from the kinetic diagram on the right. I am going to take my f of x equation and use that to get my equation of motion. I can also substitute that normal force in for mg. So I want on one side my forcing f naught sine omega t. And then on the other side, I'll have my mx double dot. Really what I'm doing is I'm moving the kx term and the mu x to the other side here. So plus a mu n sine x dot. And plus a kx. And also what I can do is I can substitute out this n because I know that that's mg. So I'll have a mu mg there. All right, so this is actually my equation of motion for my system. I'll rewrite it a little bit nicer now. So an mx double dot plus mu mg times the sine of x dot plus kx equals f naught sine omega t. Now, if we go to identify this, we are going to have this 1 degree of freedom. X is still the only dependent variable we have. And we look at our left-hand side, we have damping, or we have dissipation, in that there is an x dot term. We are going to be losing energy, but it does look different than what we had before. This is the way we have it written, nonlinear. So we cannot use the types of solution methods that we have in general for the type of system we're about to identify, where we have on the right-hand side, it's forcing, it's simple harmonic forcing, which we do know how to handle that in the case of a linear system, but not in the case of this nonlinear system. So it is going to be, I'll call it damped, but really we have this friction force happening, which we're going to know based on the approximations on the slides how to solve, or I guess, and in this problem, we're going to solve it numerically. So we can go about solving for some of these things that we need here. So we're given some information we haven't used yet. The mass of this box that's moving left and right, the stiffness of the spring, that will all go into our parameters here. The coefficient of kinetic friction, we're told. So we want A, the amplitude of the harmonic force being applied to the mass. So really part A, what it's asking us is, what is F naught? So we're given information about the steady state observations of this system. So in our parameter step, we can start to put together what is happening. Well, I guess with the identify, we at least will know that the steady state which is all we're going to be looking at here, is some x times a cosine omega t minus phi. So at steady state, we're going to have some amplitude. In this problem, we're actually told what it is. Some phase, which in this problem right now, we're not going to care, but we will come across it. And we know the driving frequency. So we are going to need to find that x, or how to calculate it at least. So based on parameters in the system, the mass is 10 kilograms, the stiffness is 4,000. Newtons per meter. So that's going to let us find the natural frequency in our system. So root k over m, our natural frequency is 20 radians per second. And the driving frequency, if we go up here, we are told that it is subjected to a harmonic frequency 2 hertz. So omega is 2 hertz. And 2 hertz is going to be 4 pi radians per second. I'll just keep it with the pi for now. We want everything in our base units. Angular frequency, always radians per second is what we want to be working with. So we can put this together because we know that for this type of friction system, the way we're going to calculate x is going to be that F naught over k, F naught we don't know at the moment, 1 minus 4 mu n, which we know is mg here, pi times F naught squared over quantity 1 minus omega squared over omega n squared squared. And we were told that when we observed this system in motion, it was oscillating with an amplitude of 40 millimeters. So 40 times 10 to the negative third meters, we already know is the amplitude. So we can put in some more things that we know, and then again, F naught is what we want to solve for here. So F naught over 4,000 times 1 minus 4 times 0.12 was the coefficient of friction that we were given. Our normal force we found was m times g, so that's going to be 98.1 newtons, since our mass is 10 times gravity. And that's going to be over pi times F naught again, which we don't know, over 1 minus, we have our driving frequency squared, which is 4 pi over 20 squared, quantity squared. And again, that is 40 millimeters. So looking at this equation, we need in part A to know what is the amplitude of the forcing term that's acting on our system. So we do have here one equation, and we do have only one known, but if we look here, F naught is unknown, but F naught also appears here. So solving this one, because our one unknown appears inside a radical and it appears outside the radical, this one, trying to solve it by hand, is not going to be very easy. And just for clarity, this whole thing is under a square root. Okay, so one equation, one unknown, but it's trapped inside a square root. So instead of trying to solve this by hand, we are going to use F0 here to solve it. So reminder for F0, one side must be 0 for F0 to work. So I have all this business on the left-hand side, and my right-hand side I want to be 40 millimeters, or 40 times 10 to the negative third meters. What I'm going to do is I can move that 40 to the left-hand side. So it's now negative, and that's equal to 0. So now this left-hand side is what I'm going to put into the F0, because when my left-hand side now is equal to 0, that means that the term, that if I move that 40 times 10 to the negative 3 back over, that means the thing I want equal to 40 times 10 to the negative 3 must be equal to 40 times 10 to the negative 3. So again, anytime we use F0, we have to have one side of our equation be 0, and that's the thing that's going to go into it. Going into MATLAB, I am putting in here all of the parameters I was given in the system, the mass, etc., the driving frequency, calculating my normal force, and calculating my omega n. So I can put everything into that equation I just had written down here, and that's what I'm doing in 258, is I am going to be trying different values of f0 until I find the one that makes this expression equal to 0. So again, just to recap, this is what I had written down. So notice over here I have minus 40 over 1,000, that's 40 millimeters, is making this expression then. I'm going to keep trying values until it's equal to 0. And I'm giving it an initial guess here. I'll just try 250 for this example. So if I run this, this is telling me that F0 should be 97.98, which is about 98 newtons. So solving this for the F0, we get that the amplitude must be about, with a little bit of rounding here, 98 newtons. What we do want to check though, because this approximation was only valid when the forcing is at least about 33% larger than the friction force, we do need to check here, even though it should have worked, but we always want to verify, is F0 over mu n greater than that 4 over pi requirement? Yeah, always a good idea to check. Since we're kind of going backwards here, this should be true. Otherwise, F0 probably would not have worked because it would have introduced an imaginary number. But let's always check when we're using this approximation. So 98 over 0.12, the normal force was 9.81 times 10. So about, those are going to cancel each other out. Is that greater than 4 over pi? And I'll do the calculation, but yes, it is. I'll verify it in MATLAB. So I'll do my calculation here. So it comes out to 8.32. Remember, that should be about 1 over 0.12. Yeah, we get about the same. And checking that against, it is definitely bigger than 4 pi, but let's just double check this. And yes, that is true. Therefore, this should be valid to use this analytic approximation. It's bigger than 4 over pi, certainly, since that's about 1.33, and this comes out to about 8.33. So at this point, we have answered part A, that applied force amplitude, 98 newtons. That's the answer to part A. All right, so what else are we interested in here? We want to compare the steady state solution analytically, which is a bit of an approximation, and we're going to compare that to the numeric solution. And then we're also going to vary the different forcing amplitudes and see how they're going to behave. So we'll start with the given one, which we just found to be 98, and then change it up from there. Okay, so for the analytic solution, well, we already have x for it being calculated. Now, when we start to vary the driving frequency and the force amplitude, x is going to change here. So we'll do that in a little bit. For right now, x is correct. So we still need to calculate the phase, that phi value. Okay, so the phi value we are going to use, again, just coming from the slides, the arctangent, 4-quadrant arctangent of that CEQ omega over k minus m omega squared. The CEQ is going to be calculated using that 4 mu n over pi omega times x. So we have all of these values now. We've calculated our x, that was that 40 millimeters. So the CEQ, the equivalent damping coefficient, we're going to get 29.8 Newton seconds per meter. Now this would let us approximate this like a viscous damper if we put in this equivalent damping coefficient for the system. Since we know that our force amplitude is sufficiently larger than the friction amplitude, we could approximate this like viscous damping. but I'm going to put this in for the value of phi, and we get that under these conditions our phi value 0.154 radians. But this phase is going to change depending on the driving frequency, and it's going to change depending on the forcing. So I'll take this phi and I'll take the x, so phi of 0.154, x at least originally is that 40 millimeters, and I'm going to put it into my steady state equation. So at least for part A, my steady state as a function of t is going to be 40 millimeters times the cosine of 4 pi t, that is the driving frequency times time, minus 0.154. And I will be able to plot that. Now, I'm going to take this, I'm going to put it aside for a moment. This is going to be my analytical solution, so I can just put that right into MATLAB and plot it. However, I want to compare this to a numerical solution, which is going to use the state space model, and it's going to be using ODE45. So where I'm going to go here, I'm going to derive this a little bit differently. I am going to take my equation of motion and I'm going to put it into state space form. So I copied the equation of motion that I had originally from the modeling step, and I will put this into state space form. I'll write that out so we don't confuse it with steady state. Okay, so state space form, I am going to be assigning state variables for this, and that is going to be determined by my left-hand side. Now looking at my left-hand side, I have an x is my only variable. I have x and its derivatives, so I need to take what is one less than the highest derivative of x. So that's going to be x double dot is my highest derivative, so all derivatives of x except for the largest one are state variables here. So I'm going to say that my x1 is x and my x2 is going to be x dot. Now I'm going to put this into a matrix form. So x1, x2, these are my state variables, are equal to x and x dot. Now if I time differentiate my state variables once, then that is going to tell me that I have x dot and x double dot here. Okay, so I want to rewrite my equation of motion in terms of only state variables. And the rule is that if I can write something as a state variable rather than the derivative of a state variable, I must do that. So I have here mx double dot. X double dot I can only write as x2 dot plus mu mg, keep that sign. X dot I can write as x2 or as x1 dot, but my rule is that if I can write it just as a non-derivative state variable, I must. So x2 plus kx, x is x1 as a state variable, equals f naught sine omega t. I can just leave like that. That's okay for what I'm going to be doing. Now the whole idea for state space form is I need to have equations to isolate the derivatives of my state variables. So I need to take this equation and I need to isolate, luckily I have only one derivative of a state variable, and that's going to be x2 dot. So I need to get that by itself. Right? So I have to move this middle term and this last term over to the right-hand side. So I'm going to have negative mu g, the m's are going to cancel out when I divide through, sine of x2, minus k over m x1, and then plus f naught sine omega t. So that is the equation for x2 dot. That's the equation for what turns out to be the acceleration. So you notice the right-hand side has only state variables, no derivatives of state variables, and it does have this explicit function of time. Now, I need also a definition for x1 dot. This is going to come from the mapping equation. So this is where I use the fact that x dot is defined as x1 here, and x dot is also x2. So this equation explicitly is going to tell my model that that is the case. x1 dot equals x2. So this is my state space model. I have my x1 dot and my x2 dot. I cannot put it into the linear form like we saw in system dynamics because I have here this nonlinear piece. I have this x2 trapped inside this sine or signum function. So I can't make that A matrix like I did for system dynamics and the B matrix and the C matrix. However, this is still state space form, and I can still put this into a state space model and put that into ODE 4.5. It need not be a linear state space model to be able to solve it numerically. Now, we can't necessarily use ODE 4.5 to solve every state space model we come up with, especially nonlinear ones, but it should be able to do a pretty good job, and that's what we're going to see here. So now, looking back in MATLAB, I'm going to create this, I'll call this driver function, which is just the state space model that I created. So let's see how this is going to work here. So we see I'm defining this thing dx, that is my x1 dot, x2 dot that I had before. So I do want to initialize this as a column vector. So if we see how dx is defined, it is a column vector. This is important because the shape of the output is going to matter. ODE 4.5 is going to expect a column as my output, as my x dot vector. All right, so that's what line 2 does, is ensure it's going to be a column vector. So line 3, this is just my x1 dot equals x2. So this is from that mapping equation. So dx is x dot, so x dot 1 equals x2 is what line 3 is showing. And then line 4, that is my x2 dot expression. So this is saying from what I wrote down, x2 dot equals negative k over m times x1 minus mu times n over m. That's the same thing as what I had, that mu g, times signum of x2 plus f naught over m times sine omega t. And just going back, again, that is what we have for this x2 dot expression. The first time I wrote this, I did forget to divide by the m, but now that m is here under that f naught. So these are the two expressions I just had. So the only job of this function here, drive 4.1, is defining my state space model. Now, I'm going to take that and I'm going to put that into ODE 4.5. So again, as a refresher, ODE 4.5 is going to numerically solve this state space model that I just created. It's going to be finding the solutions for my state variables at different points in time. So my state variables are going to be x and x dot. That's the x1 and x2 that I used. So let's see how this is going to work for us. Right, so ODE 4.5, I'm saying at t comma x, I'm defining what is my time variable t, what is my spatial variable or my state variable x. And then the name of the function that contains that state space model, that's drive 4.1, that's what we just created. And then the list of arguments it takes. So the time, it takes x, the state variable, it takes m, k, mu, driving frequency, the amplitude of the driving force, and then the normal force n. Right, so that's just how I created my drive 4.1. I really don't need, I need t and x. These other things are optional, but it's going to make this a little bit more flexible for the next part where I'm going to vary the forcing that I have. Right, so that is the function that contains the definition of the derivatives of my state variables. Then I need to tell it the time span on which to run this numerical solution. So I've defined up here, I'm using a time that is 15 forcing cycles for this demonstration. Right, so my lin space here for 15 forcing cycles of the force. Now my initial conditions, I was told that this is starting at rest. It's starting with initial conditions of 0. And one last thing here, I'm using options. Here I am using this ODE set because I want to specify a little bit tighter tolerances while it's solving this. Because this is a friction problem, it's nonlinear. Sometimes here I'm defining the relative tolerance and the absolute tolerance. That is just how much change it's looking for in my variables before it decides to stop. The default on both of these is 1 times 10 to the negative 3, so I'm making it a little bit smaller so that it tries to get a little bit more precision before it gives up and gets my numerical solution. And then I'm solving it and saving it into this XX variable, which is going to contain, well, I'll run up to this point and see what it does. Okay, so I've run it. Let's see what it gives me. So XX, it gives me 2 columns, and it always is going to be the first column is my X1, that's my position. My second column is X2, that's the velocity here. All I really care about for this problem, though, is the position, so the first column is all I'm going to use. So let's plot our analytic solution here, which is using that approximation for X and phi based on the fact that my forcing was sufficiently larger than my friction. And I'm going to compare that to my numerical solution. And I'm going to plot it and see what it looks like. So these are the results plotted. Black is the analytic solution, and red is my numeric solution. So notice they are different from each other until I get to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'll say 13 is where they are basically on top of each other, and then they even still get a little bit closer after that. But notice they're different for the first 13 forcing cycles, at least. So why is that? Well, keep in mind the analytic solution is only the steady state solution. We are not analytically finding that transient solution, at least in this course. So definitely they should disagree for the first several cycles while we're still in that transient phase. So that should be expected there. And if we look at the numeric solution, it goes up higher, it comes back down lower. It is exhibiting that transient behavior as the system starts up. And that's based again on what initial conditions we have. Here we're starting at rest. So during the transient phase, the numeric solution likely is giving us the true behavior of our system because it is accounting for those initial conditions. But then those transients, the homogeneous part of the solution appears to die off by about the 13th cycle, where now the two methods basically agree exactly with each other. Their phases match, their amplitudes match. So as the numeric solution goes into the steady state phase, what we got analytically and what we get numerically are basically the same. So this appears to do a pretty good job, the analytic method does, of approximating the steady state behavior, which will here trust our numeric solution to be the true solution here. It's just that we don't have the closed form solution for it, unfortunately, out of ODE 4.5, whereas we do have that closed form solution when we use that analytic approach. Now, for the last part, this gets just a little bit complicated, but I wanted to see what happens if I have a different forcing amplitude on this. I'm going to treat the driving frequency as constant. I'm not going to vary that. So it's just this F naught that is going to get larger or smaller. And what I'm going to do is compare what would the analytic approximation give me for my time series versus what does the numerical solution give me. Again, here I'm going to assume the numerical solution is correct. That's not necessarily true, but I'm going to assume it's more correct than the analytic solution. And this is where tightening those tolerances down above is going to be beneficial. So I'm going to look at the what the two methods yield over 50 cycles. So I am going to increase the time that I have. And I'm going to try a bunch of different forcing amplitudes. That's what FT is. So if we just see the list I want to try here, I'm trying up to 180 as the highest. I just am using these 2 lens spaces here so I get a good amount of detail for low amplitudes, and then I'm getting a little bit less detail at the higher amplitudes, and we'll see why that is. So I'm starting this at 6 newtons and then going up kind of slowly until I get to the 15 newtons, and then the spacing gets a little bit bigger. So I just want to try a lot of different of those values. And then I'm going to calculate this ratio also. So this is where I'm going to be checking, is it bigger or smaller than that 4 over pi? So I have a whole list of these ratios. So we're going to see that for the first couple, we are less than that threshold of 4 over pi, checking that, so 1.27 about. So the first couple are going to be less than that 1.27 all the way until we get around the 20th or 21st term. Then the ratio is going to be larger. So that's going to be important to note. All right, so I'm going to go into this loop, and what I'm going to be doing is I am going to be finding the amplitude and the phase for the approximate solution that, like I did before. Now that's going to change. The x and the phi are going to change based on the value of f naught I'm using. So I'm going to go one by one of those different forcing terms, and then I'm going to calculate the steady state solution according to the analytic approach. And that's what xp is going to be calculating then for every forcing amplitude I try. Then I'm going to use ODE45 and try to get that more precise numeric solution. And then what I'm going to do is I'll compare the two using the RMSE value between the 2 time series. So in general, the smaller the RMSE is, the more the 2 time series agree. So again, if we look up here, and I'm also going to look at just the steady state values. So notice I'm not using the beginning values of either of them. I'm going to start 2500 in before I start to make a comparison between the numerical solution and the analytic solution. So again, if we see here, once we get over by the end of this, the 14th cycle, that RMSE value should be pretty small because the difference between the two is low. So what I'm going to be able to do is calculate my error for each of the amplitudes I try and see what the trend is. How does the RMSE change between the numeric solution and the analytic solution as the forcing amplitude changes? So that's what I'm then going to plot down here. So let's see what this looks like. And this is what we get out. So for all of these samples, my x-axis, I'm applying that ratio of f over mu n. Remember, that should be more than 4 over pi in order to use that approximation. And then the RMSE value on the y-axis. So as a general trend, we see that the higher that ratio is, the stronger the forcing is to the force of friction, that the RMSE is getting lower and lower. That's indicating there's a better agreement between the numerical solution, which we will assume is the true solution, and that analytic approximation. So we see over here on this red line, that is that ratio of 4 over pi. Now, really, anything when the ratio is lower than that, our approximation shouldn't work at all, really, because we're getting an imaginary value. And we see that it does break down, that we're getting bad results for the analytic solution. That RMSE value is relatively, at least, very large to the left of that red line compared to the right of the red line. But even we see here, once we're right of the red line and the approximation at least doesn't give us an imaginary value, we still do have an RMSE value that is relatively large until we get to these ratios here that are going to be, let's say, around 6 or 8 times as much. Now, for this particular problem, that ratio we got was about 8.3 or so, so we're down in here. So we notice that we are fairly flat here, and that there's really good agreement in general between the numeric solution and the analytic solution. But the approximation works, but we do have to be aware that there will be some discrepancies between what we get analytically and numerically in this region between the 4 over pi and somewhere around 6 or 8 times what that ratio is.